Okay, so let me say again, I'll be substituting today and tomorrow. That's my name, Lilia Anguelova, and my office is 482, if anybody has any questions later on. So your regular lecturer actually asked me to talk to you about something else. I'm not going to continue where he left off last time. He'll continue that next week. I'll talk about some other topic that is kind of self-contained, and right now it may seem out of order, but later on you will need some of those things, and they're very interesting anyway. So I'll talk about M-theory. And actually mostly just about 11-dimensional supergravity, which is pretty much what we know about M-theory, plus a little bit more, but anyhow. So before I start going to some more details, let me first mention a few things that are kind of motivation, that explain why this is interesting to discuss. And some of you might know those things, others may not. So if you don't understand everything that I'll say in this introductory motivational part, don't worry. It's not important at this stage to follow in detail. You'll understand when to follow in detail, when I start writing. So let me just say in general, what is M-theory? So I don't know how far you've gotten in your course, but probably you've at least heard that there are actually several different kinds of string theories. At the perturbative level, when you just quantize the string, you find out that there are different kinds that are known, like type 2A, type 2B, heterotic, and such. And so it turns out that all of those are actually not different theories, or at the very least, they look different only perturbatively. But non-perturbatively, they are unified by this framework called M-theory. And they are also related to an 11-dimensional theory known as supergravity. And, well, in particular, one theory that we're going to talk about more next time, meaning tomorrow, is type 2A, which turns out that when you consider that string, type 2A, at strong coupling, you recover an 11th dimension, and then this weakly coupled 11-dimensional supergravity becomes a description of the strongly coupled type 2A string theory. So sometimes M-theory refers to the full quantum theory whose low-energy effective approximation is 11-dimensional supergravity, but other times M-theory is used to refer to the whole web of dualities that relate the different string theories to each other. So let me maybe just mention this briefly. Again, this is not yet something that you need to worry in detail. This is just still the motivational part. So there are 5 perturbative string theories. And I believe that at some point in your course, in the lectures that Freddy Cachazo is giving, you'll learn a bit more about maybe all of them, or at least 2 or 3, and you'll know what their names mean. But anyhow, at this stage, let me just tell you that there are several. And M-theory is a unifying framework for all of them. Or let's just say a duality web that relates all of them. So a duality in general means a relation between 2 theories, but the 2 theories that are related by the duality are not at the same time at weak coupling. Like in this example that I was saying, type 2A and 11-dimensional supergravity. When one theory is at weak coupling, the other is at strong coupling. So this is a powerful tool to study strongly coupled regimes of theories via different descriptions. And so at this non-perturbative level, this is really the fundamental theory. And so two of those theories, 2 string theories, namely 2A and heterotic. So for now, these are just names, but hopefully at least tomorrow you'll understand a bit more about 2A, and maybe later on in the lectures about heterotic. Heterotic E8 times C8. There are two kinds of heterotic. That's why one has to specify the group. So two string theories exhibit an 11th dimension when they're at strong coupling. And once we go to this 11-dimensional description, then at low energies, the low energy effective description is provided by this supergravity theory. So 11-dimensional supergravity, and I'll use this short quite often. So this is a standard shorthand for supergravity. And I'll use it many times for brevity. So 11-dimensional supergravity is the low energy effective description of M theory. Here, by M theory, I understand the 11-dimensional theory. As another side remark, the fundamental objects here are membranes. So in string theory, you're used to thinking about strings as fundamental objects. But it turns out that in 11 dimensions, the fundamental objects are membranes, and actually the string of string theory is obtained by somehow compactifying the membrane on one dimension. So in a sense, the string is just a membrane in which one dimension is not observable. Only at strong coupling, it becomes important enough. So these are hopefully things that make this topic somewhat interesting. So like I said, today I'll talk more about 11-dimensional supergravity. And tomorrow, we'll see how it reduces to type 2A string theory, which will also allow us to introduce the field content of type 2A string theory and say a few words about it. So actually, let me stay here. Now I'll say a bit more about 11-dimensional supergravity. And before I go further, let me also mention another thing. So today and tomorrow, I'll only be talking about massless fields. Now, when you study quantum field theory in classes, you usually talk about massive particles, because particles in nature are massive. But when we study string theory and M theory, and we talk about this being the unifying framework for all interactions in nature and the source of all particles and such, here we only study actually massless particles, because the massive states. So again, I don't know how far you are in your class, but hopefully at some point that will become clear if it's not yet. The massive states are actually very massive. So they are so massive that at any energy that is accessible on Earth, they're not excited as states. So everything arises in string theory from the massless states, from the first lowest lying level, which is massless. And then the mass arises via some other indirect effect, which actually is not that strange. If you think even in the standard model, for example, gauge fields are massless. Gauge invariance does not allow them to have mass. But we know that masses can be generated via spontaneous symmetry breaking and other effects. So here, you should have in mind that same kind of picture. The particles you study are massless, and then masses are going to arise in some other indirect ways. So in 10 dimensions and in 11 dimensions, we're only going to talk about massless particles. So now, let's see what is the field content of 11-dimensional supergravity. Actually, before that, let me also mention that 11 is actually the highest dimension in which one can have a consistent theory of supergravity, because the SUSY algebra is such, so supergravity means that it's supersymmetric, and SUSY is shorthand for supersymmetric. So the supersymmetric algebra is such that in dimensions higher than 11, there has to be a particle with spin greater than 2. And in such theories, there are various problems and inconsistencies. So 11 seems to be a quite remarkable dimension. And 11-dimensional supergravity itself is a very interesting theory. So now let's turn to that. And now I begin being more concrete. So now you should pay more attention. So now, what is the field content of this theory? And if you have questions, you can ask at any time. Since it's a supergravity, meaning it contains gravity, there has to be the metric as one of the fields, which is going to give us the graviton when it's quantized. And let me also write this in general, that indices Mn are going to be 11-dimensional indices. So they go from 0 to 10, where 0 as usual is time. So they run over 11 values. Now then there is another field that has both a vector index and a spinor index. And this is a spin 3/2 field. Spin 3/2 fermion. That is the supersymmetric partner of the graviton, so it's called gravitino. And finally, there is another field that is a 3-form, or a 3-index antisymmetric tensor. Yeah?
Highest dimension available is that if we have higher dimensions, then we would have particles with the spin more than
greater than 2.
So why that's a problem?
No, I'm not going to explain here why it's a problem, but there are various inconsistencies with higher dimensional spin theories, unless you have all spins, meaning infinitely many, all higher spins. But that's really what string theory is giving, actually. So string theory is the only consistent theory of spin greater than 2, because it has infinitely many. Whereas any finite quantum field theory would have only a finite number of fields, and so only up to 2 gives you a consistent theory. I cannot prove that here, it's an involved thing, but it's a true statement. So antisymmetric. Or a 3-form potential. So some of you may know there are also other supergravities that live in less than 11 dimensions. In fact, in any 10, 9, any dimension, less than 11. And the only common thing is that in every supergravity theory, there is always the graviton and the supersymmetric partner, the gravitino. But with different dimensions and with different amounts of supersymmetry, there may be various other fields that complete the supergravity multiplet. So all of those fields here form just one supermultiplet, meaning that supersymmetry transforms all of them into each other. So I'm not going to discuss in detail the Susy transformations, but we'll spend some time talking more about those fields. So let's count the degrees of freedom in each of those fields so that we can see that the number of bosonic and the number of fermionic degrees of freedom are equal, which is a key feature for a supersymmetric theory. So in any theory with supersymmetry, one always has to have the same number of physical degrees of freedom for bosonic and fermionic particles. So, okay, let me also write that so that you know where I'm going. So let's count the physical degrees of freedom, or polarizations. So this is equivalent word, polarizations. for each of those fields. For example, yeah? In 11 dimensions, that will be just n equals 1. So yeah, I wanted to mention this. For example, thinking 4 dimensions, if you think about the electromagnetic field, which is described as a one-form potential, then you know that there are 4 components, but there are only 2 physical degrees of freedom, only 2 polarizations. So similarly, in various other dimensions and all other fields, the number of components is not equal to the number of physical degrees of freedom. So let's now count how many are the actual physical degrees of freedom. And well, to do that, one has to recall that we classify particles according to the irreducible representations of the little group, which is the subgroup of the Lorentz group that preserves the momentum. So in d dimensions, d of course here is 11, but let me be more general for now. So in d dimensions, I think it's a bit more illuminating to stay general as long as possible. The little group. Yeah?
I mean, pointer invariance in your theory, right?
Yeah.
But if you have a general manifold with some curvature and so on, you don't really have pointer invariance on it. So do you talk about it?
Considering yet any background, we're just classifying the states.
Okay. So,
right? So that's also what you do in 4-dimensional quantum field theory. So for this purpose, think about 11-dimensional Minkowski space, and you just want to classify the states that each of those fields is going to have. So, and indeed, since we are now in d dimensions, so the little group is going to be S of d minus 2. So indeed, so the Lorentz group will be S of d, and the little group, like again in 4 dimensions, the little group is going to be S of 2, which would mean that for a vector potential that has 4 components, it has to be, the number of degrees of freedom has to be actually the components of SO2, which is 2. So these are the 2 physical polarizations of a vector. If people don't remember much about that, I'll remind you in another way of doing counting in a moment, but this is shorter, so let me first do this, and then I'll review something else. It is slightly longer, but maybe more physical. So let's start with the graviton. So the metric is always a symmetric matrix. And now, since the little group is S of d minus 2, which here is S of 9, so we need to count actually the components. So the symmetric, okay, let me write the whole thing. So the number of independent degrees of freedom, number of independent degrees of freedom is equal to the number of components of a symmetric traceless d minus 2 by d minus 2 matrix. Okay, so this is still the graviton. So that then means that the number of degrees of freedom let me just abbreviate degrees of freedom that way, is going to be 1/2 d minus 1 times d minus 2 minus 1. So this is just the components, the number of components of d minus 2 by d minus 2. These are the independent components, symmetric matrix. And this is the trace, which we have to subtract to have irreducible representation. So now this actually gives 1/2 d times d minus 3. So this is, in general, in any dimension d, this is how many polarizations a graviton has. Now, in 11 dimensions, this gives, so we obtain that the graviton in 11 dimensions has 44 polarizations. Is it funny? Or is there a question? Okay. So go here. So let me, as an aside, mention another way of counting the degrees of freedom. Maybe it's not necessary, maybe everybody remembers the little group, but just in case somebody doesn't, this may be a little bit more physical. Or it's equivalent, of course, it's the same thing, but it just makes more explicit what the little group does for us, or how it does it. So as an aside, let me just mention briefly how to counting polarizations or degrees of freedom without mentioning the little group. I'll keep mentioning it for the other fields, but it's maybe more illuminating to mention this once. So the basic thing that the little group does for us, and the basic thing we want, is the following. Well, the number of degrees of freedom is the number of components of whatever field we're studying minus all the kinds of gauge invariances that we have, minus the number of gauge invariances. Because each gauge invariance, or each parameter of a gauge invariance, can be used to remove one component. So it reduces the number of independent degrees of freedom. And as an example, think about, so this is the basic thing that we want to count the number of degrees of freedom. We want to be able to remove gauge artifacts. And that automatically happens if we just talk about the little group. But let's do it in one example without talking about the little group, which is an example that is slightly simpler than the metric, but the principle is the same. And so let's look at the example of electromagnetic field in d dimensions. If you want to think about electromagnetic field in 4 dimensions. So, well, we know that it's described by a vector potential with an index running from 0, which is time, until d minus 1. And we know that there is a gauge invariance namely invariance after the following shift, under the following shift. If we shift the vector potential by the derivative of some function. this is a function. So we know that the action is invariant under such transformations. So, well, this is one parameter. So we can remove one degree of freedom by doing a gauge transformation. So -1 from here. And however, one can notice that there is a residual gauge invariance because, well, okay, let me be a bit more detailed. So usually people choose, and let me also do that, Lorentz gauge. So choose the gauge d mu a mu, well, dm am equals 0. Now we can see that if we transform the potential in this way here, then there will be a residual gauge invariance for functions lambda that satisfy this equation. So such functions lambda would not be affected. So the gauge would still be preserved, but we have this arbitrary option still. So in order to see what's the meaning of this, it's more illuminating to go to momentum space. Actually, those who remember well the electromagnetism in four-dimensional quantum field theory probably already know that this is going to lead to also the longitudinal polarization being unphysical. But we'll see that more clearly in momentum space. So let's transform to momentum space. So I'll skip some overall factors of pi and such. Let me just write integral over momenta. And this is some polarization vector. Or you can think of this as a superposition of plane waves, if you don't want to think about transforming to momentum space. So then the gauge condition becomes, so instead of dm am equals 0, now we have pm. So this is the gauge condition now, and the field equation, or equation of motion, and actually, to have this equation of motion, one already has to use this gauge choice. Otherwise, there will be some other term proportional to this condition. So the field equation, probably people remember that, but anyhow, let me go on. Then looks like this. It's just a statement that it's a momentum squared is 0, so that's a massless particle. And now we can see what is the meaning of the residual gauge transformation. Namely, if we now shift the polarization vector by some function times the momentum, then let me denote this as the new polarization vector epsilon prime. So then we still have that the gauge condition is satisfied. We still have epsilon prime contracted with the momentum is 0, but once we impose the field equation due to, so this is called on shell, meaning only for solutions of the field equation. So it's because the shift is proportional to the momentum itself, so once we contract the whole expression with P, this term vanishes due to the field equation. So we see that anything proportional to the momentum is exactly this residual gauge freedom, and it's still a gauge artifact. It's also not a physical degree of freedom. So we can remove such a component just by doing such a shift. So we see that way that the longitudinal component, longitudinal meaning proportional to the momentum, is also not physical. And that's very well known in, say, in 4 dimensions. This is just the statement that the temporal and longitudinal components are not physical. Of the electromagnetic potential are not physical. So we have only 2 physical degrees of freedom, or 2 polarizations. So this is well known in 4 dimensions. Now, in D dimensions, this just means that we have D minus 2 polarizations for a vector field or for an electromagnetic field in D dimensions. Now, we could have done something like that for the metric also, but you see it's much more complicated and much longer than just talk about the little group. So like I said, for the other fields, I'm only going to talk about the little group. But what is the difference for the metric is that in the case of the metric, the gauge parameter is actually carries an index also, because gauge transformations there are general coordinate transformations. So, so here, one gauge parameter allowed us to remove 2 degrees of freedom, whereas for the metric, a vector gauge parameter is going to allow us to remove 2 times d degrees of freedom. And this is going to give us exactly the number that we obtained from the counting with the little group, which was 44. So hopefully that makes things more clear. If not, let me know. So now I'm turning to the next field, which was, yeah?
Temporal component?
Okay, I didn't do it explicitly, but like I was saying, originally with the gauge condition dm am equals 0, well, by fixing a gauge, we already remove 1 degree of freedom. So usually we take that to be the temporal component. And then we can see that one more component is physical, which turns out to be the one proportional to the momentum. So in 4 dimensions, these are temporal and longitudinal. In D dimensions again, but then we are left with D minus 2. Okay, since I was mentioning about the metric, let me just for a moment divert here. So in the case of the metric, the gauge invariance is with respect to a transformation like this, with some parameter that carries index. And so choosing a gauge removes d degrees of freedom, because this value goes from 1 over, runs over d values, this index. So this is epsilon m is the analog of just lambda there. And then the residual gauge transformation the residual gauge invariance removes, again, the more degrees of freedom. So then the counting here is going to be just, so in d dimensions, d times d plus 1 over 2 minus d minus d. And this should equal to the same formula there, unless I made some typo or mistake. Anyhow, you can check this and let me know if it doesn't work. But that's the main difference between the gravitational case and just the electromagnetic field. I guess I'm going slow, maybe. So let me turn to the next field, which is the gravitino. Maybe it's going to go faster. Any other questions? So the gravitino carries two indices, so it's a vector spinor. So let me write it again. So it has a vector index, just like the electromagnetic potential. But it also has another index, which is a spinor. So a regular fermion would have, say, like the electron, would have just one spinor index, no vector index, right? But the gravitino is a more involved object, and it has both kinds of indices. Like I said, it's called vector spinor. So again, the little group here is SO d minus 2, which, since we're in 11 dimensions, is SO9. So this, now we have to count the independent degrees of freedom for a spinor and a vector in 9-dimensional space. So for a vector, vector of SO9, there are 9 components. It's the same counting that we had above, where we had d minus 2 components because we're in 11 dimensions, and now we have little group SO9 and 9 components. So for the vector, everything is like above. Now, we also have a spinor. And this is slightly imprecise. Actually, when talking about spinors, one should say that the group is not SO9, but spin 9. But I don't know how many of you know about that. Anyhow, it's not very important. Just for any group SON, there is a corresponding spin group that is related to spinors. And you can think of it as some kind of a double cover of the SON group. So remember that in the maybe very first time you've talked about spinors in quantum mechanics or whatever, quantum field theory, they were explained like something that has to be rotated twice the full rotation in order to be the same. So this is this notion that the spin group is a double cover of SO9. Well, actually, the whole thing is about how you construct representations. So this is just in terms of gamma matrices, right? How the Lorentz group acts on things. So for vectors and tensors, we use SO9 because we can directly construct the representations of the Lorentz group on those fields. For spinors, the representations we construct via gamma matrices. And so they also give representations exactly of the spin group.
Okay, is the spin group also, is it simple connected or something? Because that's the difference, I think, between SO3 and SU2. That SU2 is simple connected or something like that. Yeah? Okay.
Well,
Is that true for higher spin groups as well?
I'm not sure if it always has to be true, but I think that up to here it is.
I think that's the definition of the spin group, that it is the universal cover of the SON group.
Yeah,
spin N
indeed,
group,
that's a general.
which is the smallest and also actually the largest simply connected group which covers. So it is simply connected.
Okay. So, okay. So the number of components here will be 2 raised to 8 over 2. Since this is odd dimension, we go to the lower even dimension. So that's 2 to the 4 means 16. Okay, so in order to count the degrees of freedom here, we have, okay, so psi is a tensor product. So we have 9 times 16 components. However, in addition to just having a spinor index and a vector index, this field, this new field, gravitino, has another gauge invariance that we have not taken into account yet. And that's related to the action. So let me write this. Well, there is one more gauge invariance. So we'll have to subtract something from here. And to understand that, let's look at the action for this field. So up to some constant that I don't remember. It's of the following form, psi bar. Here I'll suppress the spinor indices. And this is contracted with, now this is a product of 3 gamma matrices, anti-symmetrized with respect to all 3 indices. Are people familiar with this notation, or? So this is anti-symmetric. Let me write the whole thing. Anti-symmetrized product of 3 gamma matrices. So for just a regular fermion, there is only, well, there's only one gamma matrix, so this additional gauge invariance is not going to occur. But now, because there is this anti-symmetry, if we transform, now this is the gauge invariance. If we transform the field in the following way, where this is a derivative on some parameter, so since there is also a spinor index, this is also a spinor. Yeah. Oh. Oh, that's probably. Can you see down there? Can you see the lower end? So, okay, let me continue here. So what I was trying to say there is that because there is a product of three gamma matrices that are anti-symmetrized, when we transform by a derivative of something, then we're going to have two derivatives on epsilon times this gamma m and p. So that's going to be 0 because we multiply something anti-symmetric with something symmetric. So that's a gauge invariance for that action that is not present for just a spinor. So, okay, let me write also here. So there is the following gauge invariance. If we transform the gravitino as derivative of some spinor, then the gravitino action is going to be invariant, actually up to some boundary terms. But we are going to ignore them here because for these purposes we are just considering flat space infinite. For the more curious, I should say that those boundary terms do play some role in some special cases. Like I was mentioning heterotic C8 times C8, in that case they're actually boundaries. And the fact that the symmetry is only up to a boundary term reflects something that on those boundaries there have to be some additional gauge fields that are actually the E8 gauge fields. So that's how M theory on some manifold without boundaries gets related to heterotic string theory. So anyhow, in cases when there are boundaries, this plays an important role. But for the moment, there's no boundary, so there is this gauge invariance. And that means that, so the number of degrees of freedom was up to now 9 times 16. And now we need to subtract 16 from this spinor, which here is a gauge parameter for this new gauge invariance. So the number of degrees of freedom of the gravitino is equal to 8 times 16, which is 128. So these are the number of polarizations for a gravitino in 11 dimensions. And, well, following the same kinds of considerations, you can compute in any dimension. Yeah?
Your gauge freedom acting, gauge conditions acting twice. Here it only acts once. Is there some reason for that? Or? I mean, you had the residual gauge invariance previously, and this time somehow.
Yeah, but here I don't see how you would have anything residual.
Excuse me?
Because here there is no constraint. I'm not choosing any gauge here, right? I just check that if I substitute this transformation in the action, it's going to be invariant. So epsilon can be anything, all 16 components. There is no restriction on that. Whereas for the other gauge choice, I could see that when I substituted in the gauge choice, it was not fixing the whole freedom of the parameter. Like for a vector field, for an electromagnetic field, if the parameter was still satisfying the Klein-Gordon equation, that would not change the gauge, but that would still be arbitrary parameter, right? I don't know whether that's still somewhere here. Like for the gauge field, there was a residual gauge freedom for a parameter satisfying this equation. Choosing the gauge was not fixing a parameter like that. So that's why I could remove double. Whereas here, epsilon can be anything. There is no restriction on that. So I removed the whole number of components. Yeah?
In fact, there is a residual gauge invariance because you can take the gamma trace of the spinor and it gives you 0.
Can you say again?
The gamma trace. You can contract the spinor with the gamma matrix.
Ah, okay.
And in fact, so this invariance with the derivative, you already commit with the Witten group. But the residual gauge invariance is the same that to say that with the matrix it's traceless.
I've already counted the traces of the...
Yes, but here you didn't count the traceless, and if you count that you don't have trace, it will give you something.
Oh, okay. Yeah, of course. So just like for the metric, it's important. So actually, in principle, yeah. So I didn't want to go into such details, but in principle, people introduce something that is minus some, well, up to some coefficients, whatever. So some kind of a traceless gravitino also, just like for the metric. But ultimately, things work out. It's just a rearrangement of arguments. So. But yeah, that's also, indeed, in general, the statement that the physical degrees of freedom are always traces, always transfers. And actually, I think that that's already taken into account in the fact that I was considering SOD minus 2, meaning SO9. Because that comes already from being transfers to the momentum. So indeed, I don't think that I took that into account before. I think that that's new compared to what I took into account by talking about the little group. Because the little group is already talking about, no, okay, it's transfers, about the traces.
Because if I remember, when you take the action of the Rarita-Schwinger field, then you can impose this derivative condition, and after, with the equation of motion, you can impose the Traskas condition. But it's the last condition, so I think that this gauge is already taken into account in SOD-2, and then later we have to add the Traskas condition.
Those degrees of freedom by themselves will describe just a spinor, right? So, how should I say? The representation that we would have initially would not be reducible. It would contain a gravitino and a spinor. So we need to remove the spinor in order to have just the gravitino. So I did not present it in that way, but again, there are different ways of explaining the same thing.
It just seems that if you were considering Hamiltonian description of this, and then you were looking at phase space and looking at slices of phase space on which you're on the subspace on which you have your gauge invariance, then there it always, and then you have gauge orbits and so on. So there you kind of impose your gauge invariant gauge condition twice. That always gives you. It removes twice the number of degrees of freedom the way you have it here. So it just seems to me really natural that you would have it removed again.
If they are fifth class constraints, you subtract it twice. But if they are second class constraints,
So it's the second class, huh?
Okay, maybe I'll think about this more. Let me just finish with the free-form field, because I'm going to stop. Let's move here. Yeah, I think that probably the traceless should be contained already in SOD minus 2 because we're counting irreducible representations. Well, okay, I don't know. I'll try to answer that tomorrow. So the final field is the 3 form. And this time we'll count very fast, so the number of polarizations is equal to, well, the number of independent components of rank 3 anti-symmetric matrix in D-2, which now is 9 dimensions. So it's just going to be 9 times 8 times 7 divided by 3 factorial. So this should be easy to understand since the matrix is, the field is anti-symmetric. So the first index can take 9 values. The moment we have chosen some value, there are only 8 possibilities for the second. And then once we've chosen those 2, there are only 7 for the third. And there are 3 of them, so there are 6 permutations, which is taken into account by dividing by 3 factorial. So this is the total number, which is 84. And I guess I'll take 5 more minutes. So now we can count degrees of freedom in 11 dimensional supergravity. Now the bosonic degrees of freedom are equal to those 84 plus the 44 we got from the metric, which is still up there. And so we get 128, which is the same as the gravitino. So they're equal. That's the basic message, which should be true for any supersymmetric theory. Yeah? Yeah. So when you quantize it, just like when you quantize the metric, you find the gravitons, when you quantize the gravitino. So this is like quantizing the electromagnetic field, but instead of, this is a 3-form potential. Instead of 1 index, it has 3 indices. So this is like some kind of a generalization of electromagnetic field. And later on in string theory, you'll see not just 3-form, but various other forms, 2, 4, and whatever, or 1, 3, and depending on whether you're in type 2A or type 2B, there will be even or odd, various kinds of P-forms in general. So there will be some kind of generalizations of the electromagnetic field whose potential is not 1 form, but a higher form. Well, the spin is like usual. Say the spin of the graviton is 2, the spin of the gravitino is 3/2, and this is spin 1. So these are, so this is the potential. And it has a field strength, that is a 4-form. And as a form, this 4-form is just equal to d of this 3-form potential. So this is the basic relation that you know from electromagnetism, just that in that case, the potential is a 1-form, and so the field strength is a 2-form. In string and empty, you have various other forms that just have more indices. But other than that, you can think of them as some kind of electromagnetic fields. And also there will be electric-magnetic dualities between them, just like for electric and magnetic fields in 4 dimensions. So what else did I want to say? Okay, let me write the action of 11-dimensional supergravity, and that will be the end. And tomorrow, mostly, we'll be reducing this action to 10 dimensions and obtaining type 2A string theory, the low-energy effective action of type 2A string theory. So action, I'll only write the bosonic part. The fermionic completion is a bit more involved. It does not include just the gravitino term, but various other couplings. So for brevity, I'll just write the bosonic part, and that's also what mostly you'll need if you need anything of this. So we have 1/2 kappa squared. So usually this is related to the Newton constant. The convention is this 16 pi G11, where G11 is Newton's constant in 11 dimensions. D11x square root of determinant. Then there is the Ricci scalar curvature minus 1/2 F4 square, where F4 is this. So F4 is D of the 3-form potential. And then there is a so-called Chern-Simons term, which is A3 wedge F4 wedge F4. And finally, let me write F4 squared means the usual thing, 1/4 factorial F M1 M4 F N1 N4 contracted with the metric G M1 N1 G M4 N4. And actually here you can see another thing that makes a difference if you have a manifold with boundaries. Namely, just like for the electromagnetic field, there was a gauge invariance related to the 1-form potential. Here the 3-form potential has a gauge invariance related to some 2-form parameter. But now, if you have a manifold with boundary, well, the field strength would be invariant, but the potential will not be. So again, when you consider, say, the case of heterotic strings, again, the relation goes through some boundary terms, and this affects things somehow. So again, this is also invariant up to boundary terms. Okay, any questions other than the one about the gravitino? Yeah?
It seems to me that if the A has spin 1 and the graviton has spin 2 and we all have an equals 1 supersymmetry, it's not possible to connect the A to the graviton by using the supersymmetry generator. Or is it?
I don't know, maybe you're thinking about 4 dimensions or something.
Yeah, it's possible. Right, we're just using the
But
4 dimension.
all of those fields belong to the same supermultiplet in 11 dimensions. Besides, recall that when you say n equals 1, that means, say, in 11 dimensions, the Susi parameter actually has 32 components. So it's like having 32 supercharges. what is n equals 1 in higher dimensions is not what is n equals 1 in 4 dimensions. And when you reduce higher dimensional n equals 1 to lower dimensions, you get more and more, well, at most, I guess, you get n equals 8 regarding 4 dimensions.
But for example, if you were to do a sushi infinitesimal transformation on the 3-4 potential, how will it change? Will it?
So I don't remember the transformations here, but like in general, the fermionic fields transform to the bosonic and so forth. So I think the sushi variation of the gravitino is something like, so there is a term that is just directly the sushi parameter, and plus some other term that contains, I don't remember exactly the contractions and numerical factors, but it contains this 4-form field. Again, and somehow it's some gamma matrices, and then also the spinor will contract it with that. So I don't know, maybe a guess could be something like that, and 4 and say gamma. Again, probably after some numerical factors. This will be here. After some coefficient. So the fermionic field goes into, well, the metric also implicitly enters here. So it goes into a combination of the two bosonic fields. And each of the bosonic fields goes into the fermionic field. Any other questions?